Welcome to this video. I'm joined here by the Agate AT2040 and the Adash analyzers. In this video, I wanted to explain why it's better to use a simulation feature than it is to use the mechanical shaker when verifying the performance of analyzers when you are checking your cabling or setting up your control room equipment. So to illustrate this, I have the mechanical shaker right here. Um, this shaker right here has been around for about 30 years. It's probably the best there is, and I think that this is the same mechanical shaker that's found in most portable vibration calibrators. And I also have an accelerometer here, so you can see how you would mount the accelerometer on top. It would be just like this. So you may be thinking to check the performance of the analyzer. What you would do is you would shake the accelerometer, and then you would view the readout on the analyzer. But that's not necessarily the best way to do things, and I'm going to demonstrate why. The first reason is because of a heavy mass load, you would not be able to shake the mechanical shaker in frequencies that you desire. For example, I have this CA303 here. This is about 500 grams, and with this 500 gram sensor, when it's mounted on top, the mechanical shaker cannot shake above 1,000 hertz. It's just not possible. It's limited due to its size. The second thing is just the mechanical shaker by itself, with no payload or a light payload, cannot do a full frequency range at high G levels. For example, you would not be able to do 10,000 hertz at 20 Gs. You would not be able to do 5 hertz at 10 Gs. There are just some things that you cannot do due to its size. And lastly, accuracy. When you have the mechanical shaker inside the AT2040, that's the 3% error. When you have the accelerometer on top, the accelerometer is a 5% error. So you're now looking at a 8% error minimum if you were to use the mechanical shaker into the analyzer. However, if you were using the simulator, you are eliminating the 5% source of error from the accelerometer, and you are eliminating the 3% source of error from the mechanical shaker, and you have lowered yourself to less than 1% error. Okay, so let me demonstrate this using the signal analyzer box. So we're going to go ahead and start the shaker at 10 Gs, 100 hertz. And we can see that the shaker has no problem doing 10 Gs at 100 hertz. In fact, the specs say that we can go up to 20 Gs at 100 hertz. But let's try something different. Let's try stopping this and setting this to 10 Gs at 20 hertz. Now we can see in the picture that the shaker is shaking its little heart out over there, and it's trying its best, but no matter what, it cannot get above 4 Gs. And that's because it's at maximum displacement. And you can see that designated in the middle bar graph on the shaker screen right here. It says that the shaker is at maximum displacement, and it will not go any further. So let's go ahead and stop that. And let's again set this to 1 G at 5,000 hertz. So we can see now that the shaker is at 1 G, 5,000 hertz, and we're not having any issues. However, let me set this to 10 Gs. Now we can see at a setting of 10 Gs, 5,000 Hertz, the shaker is only able to do 7.61 Gs. And again, this is because of the limitations in the mechanical shaker. When you have additional weight on top of it, such as a large sensor like I showed earlier, like the CA303 or anything that's around 500 grams, you won't be able to go above 1,000 Hertz. Now what I've done is I've disconnected the accelerometer and I've removed it, and I've connected the signal analyzer box to the simulator output. And we're going to do the same test, but instead of shaking the accelerometer mechanically, we're going to simulate it. So to do so, I will go to Simulation Signals, and I'm going to select that same accelerometer we were using, which was the Dytran 3010 M112. And I'm going to go ahead and start the shaker. And we can see the 1G signal appearing on the shaker, or on the analyzer, sorry. And I will go ahead and increase this to 10 Gs. And in fact, I can increase this to 99. I can probably even go up to 150. I think the limitation on this is somewhere around 160 Gs, but it depends on what type of sensor you're simulating. This happens to be a 10 millivolt per G sensor, and so I can get about 160 Gs, but currently we're doing 150 Gs. So as you can see, simulating signal gives you a much broader range to work with. So let's go to the other measurement, which was 10 Gs at 20 Hertz. We were not able to do that earlier. And you can see that we're simulating 10 Gs at 20 Hertz with no problem. And again, we can go up to 150 Gs, like I just showed you. And then to demonstrate the other frequency we were not able to do was 5,000 at 10 Gs. And you can see that we are simulating the 10 Gs at 5,000 Hertz now. So as you can see, the simulator is an extremely valuable tool when you are connected to any type of analyzer box, or you are projecting a signal through cabling. Anything that you want to do to avoid using the mechanical shaker due to its limitations, you can do with the simulator.